Mrs. Anderson here. So I missed example 2 and I wanted to go back and explain it because a couple important things happen in example 2. So I have gone ahead and put my data in the table. I have the number of sides and the number of diagonals. I put the number of sides for a polygon in my X column and then the diagonals in my Y column. So a polygon with 3 sides has 0 diagonals, would be like a triangle. Polygon with 4 sides has 2 diagonals, like a square, etc. So I have my scatter plot over here, you can see. So it kind of looks like this. It's all in the first quadrant, and it looks like half of a parabola. So now I'm going to go and look at my other data points, or my other data. So when you're deciding what regression equation to use, the first thing I look at is the R-squared values. So R-squared for the linear is 0.96. But this clearly doesn't look like a straight line, nor does the data increase at a constant rate. So I know it's not going to be linear. So I'm going to go down, and I have an R-squared value of 1 for my quadratic. That means it's almost a perfect fit model. If I turn that on, you can see that the model goes through every point exactly. So that's why my R-squared is equal to 1. It's an exact match. So this would be my model here that I'd want to use. But if I look down at cubic and quartic, I also notice that R-squared is equal to 1. So then I need to decide, well, which would be better, cubic, quartic, or R-squared? So after finding the R-squared value, the next thing I look at is the A value. And for this particular examples, if you look at this A value, I have a negative 1.3906 times 10 to the negative 16th. When you see something like this, it's in scientific notation, which means this A value actually has 16 zeros before this 1.9, like it would be 0.000016 zeros, then 13906. And if you were to round that number with 16 zeros behind a decimal, it would round to just 0, which means that the cubic example doesn't make sense because your A value would be 0. And if you had 0x² or x cubes, you'd really just have a quadratic equation after all. So I'm not going to choose this. It's the same argument for quartic. My A and B are both 0. They'd round to 0. And if you look at the B and C and the C and D values, they're the same as my quadratic model. So that also verifies that in fact this is a quadratic equation. Then my C value for this quadratic is 0 as well, if you were to round this value. So when you get a really small number like that, that means it's 0. So my equation here would be f of x equals, it'd be 0.5x squared minus 1.5x. And my constant rounds to 0. So that would be the equation there. Then correlation coefficient really is just the R value. And there is no R for this one because it's quadratic. So I actually have just a coefficient of determination. So you'll notice only the linear model gives me an R value. A correlation coefficient only applies to linear. And then the other ones don't list R. So I have no R, but my coefficient of determination is my R-squared, and that would be equal to 1 in this case. So I just wanted to cover that quick because I wanted you to know, if you see this scientific notation, essentially it means that this value is 0. Okay,